Hi, everybody. This is about adiabatic and isothermal processes. Okay, so real quick, right? Keep this simple. What is the difference between adiabatic and isothermal? Well, adiabatic heat transfer is zero. So delta E total is the work done. If you compress something, what happens is P goes up because less space. This has no effect on the temperature. This does not. The temperature goes up from a separate process. That's what I mean. This pressure going up has no effect on temperature. A lot of people mix this up. They say, oh, the pressure goes up, therefore the temperature goes up. Pressure does not cause temperature, guys. Remember, PV equals nRT is a mathematical relationship, not a causal relationship. T and V affect pressure, and N, of course. Pressure does not affect these. Now, if I apply an external pressure that does work on the fluid, that's different. I mean, the internal pressure increasing of the gas doesn't affect its temperature, right? So this has no effect on temperature. The temperature does increase by a separate process because of the work added by the walls colliding with the molecules. And when we did this in class with the book, right? If the book is pushing on the tennis ball, it adds energy. If it's expanding away, it takes energy away. So expansion, expanding, compress, expand. What word are we going to use here? Compression. I'm going to use expansion. Colons right there. Compression, expansion. If I expand, pressure drops because more space. Also, that has no effect on temperature. That's not why it gets cooler. It gets cooler because work is removed or subtracted by the walls colliding with molecules. So here the wall is going into the molecule. Here the wall is moving away from the molecule, and therefore it's going to take energy away. Great. That's adiabatic. Heat is zero. So therefore the total energy change will be entirely by this process of the work added or the work removed. Remember, delta E total is the change in temperature. That's 5/2 N R delta T is entirely by work. Isothermal, so to do this, we need insulated for an adiabatic. It must be insulated. Otherwise, heat would step in and add energy or take energy away. That's what happens in isothermal. Isothermal is not insulated. That's the difference. Just like with isochoric, it's rigid. With isobaric, it's not rigid. And you're using heat to create a pressure, which either expands or doesn't. This one has to do with insulation. It's either insulated or not. Now, if it then you apply an external force. So both of these are external pressure driven. Sorry for my messiness. External pressure driven. Whereas isobaric and isochoric are heat driven. So if I compress or expand here, the pressure goes up because less space. And what happens is at first, the temperature goes up because work, right, is positive. But it's let out via heat because it's not insulated, right? So it equalizes. Just like in isobaric, the pressure goes up, which expands the balloon or expands the bottle or expands whatever you're heating in isobaric. But remember, the pressure equalizes. Here it's the temperature that's equalizing. It does go up because you're compressing it. You compress something, the temperature goes up because work is being added by the walls. So what happens here is that isothermal is delta E total is 0, but Q equals negative W. In other words, the heat balances the work. If the work adds 10 joules, the heat takes away 10 joules. Done. Right? If work is positive 10, Q says, I'll just take that away. So T is constant. I hope that makes sense. Expansion is just the opposite. Pressure goes down because more space. And so therefore we just have P1V1 equals P2V2. We're going to derive a similar formula for adiabatic in a second. T goes down because work is negative, but it is let in via heat. So it equalizes. Again, if W is negative 20, then Q will be positive 20. So T is constant. Done. That's the quick notes for isothermal and adiabatic. Pause this if you need to. I hope this makes sense. Rewind it. I just explained it all. Hope it makes sense. I'm not doing the drawings here. We'll do those in class. Sorry if you missed those, but this is the notes. You can, based on everything we've been doing, you actually can draw this in your own way. So I don't need to repeat that. Now, bonus. That was the notes. You can stop now if you want. But if you want some math. Oh, and actually, there's an equation here that you should write down at the end. Derivation. So work is actually negative the integral of pressure dV, where pressure is a function of volume. For those of you who know integrals, the point is instead of negative P delta V, the delta V turns into dV, and this ends up being, has to be a function of volume. And the reason why this is important is, say you have an isothermal. Pressure is nRT over V, right? These are the isotherms, right? These are constants. So I have pressure is constant over volume, right? And that's this. It's a graph of a hyperbola of an inverse function. So how do I add up all the little pressure? There's a pressure there, there's a pressure there, there's a pressure there, there's a pressure there. And this is the volume. So say this is my delta V from here to here, 0.1 to 0.2, and I have an isothermal expansion. How do I do that? How do I do pressure delta V? Well, what I have to do is I have to do an instantaneous pressure times dV, and I have to do another instantaneous pressure times dV, where dV goes to 0. We take the limit as this delta V goes to 0, and we call the differential, which is called dV. Those of you who've taken calculus should know exactly what I'm talking about. I'm somewhat deriving calculus right now, or like re-deriving calculus right now, but I'm doing it fast, so this is not comprehensive. So if you have no idea what I'm talking about, take a calculus course, it's great. If you want to stay with me though, that's great too. So the point is, we do a pressure times delta V, infinitesimally small, and we add them up. That's called an integral. We take the sum, this big S is sum, of the pressure at any given point times its delta V going to 0, which we call the differential dV. Isn't that cool, right? So for isothermal, right, isothermal, work is negative nRT over V dV. nRT is constant, so it comes out. So we get negative nRT times the integral of dV over V, and this is the natural log of V. So we get negative nRT ln V, but we need to evaluate it from V1 to V2. So we do natural log of V2 minus the natural log of V1. And as you might know, that's negative nRT of ln V2 minus V1. And then we actually put the negative inside to make it to the -1 power. So we actually then switch it to negative nRT, sorry, positive nRT ln V1 over V2. And so the work done by an isothermal function is a natural log function of the ratio of the volumes. Isn't that cool? Is that intuitive? I don't think so. I mean, it sort of mathematically makes sense because it's an inverse function and we're taking the integral of it. We're taking the area under the curve, right? So we also realize that work is area under PV graph. That's pretty cool. It's actually a big deal, right? So this is the function for isothermal. And I think I did it right. If I did some calculus thing funny here, let me know. But I think this is right. And we wouldn't put this in the power. We just keep that up front. Kind of cool, right? Now let's do adiabatic. This one's fun, right? So this one actually comes from this. So yes, PV equals nRT, right? But T isn't constant here. In adiabatic, P1 V1 over T1 equals P2 V2 over T2 because they're all changing. So how do we do that? Here's how. You ready? This one's cool. So work is negative integral of P dV, right? So we need to substitute in for P. You might think we do that, but then how do we substitute in for T? What do we plug in for T? Well, here's where we go. We go to that the differential of E total is 5 halves for air, NR, the differential for T, where the delta turns into D, the differential as delta something, like delta T approaches 0. We take the infinitesimal change in T, or the infinitesimal change in energy is this. So this is where we start. The next part is, because Q is 0, delta E total is work, which means dE total is dW, the infinitesimal increase or decrease of work, which is just negative P dV. So we have this go into here. So we have negative P dV equals 5 halves NR dt. All right, isn't that cool? Right? And then we plug in P, right? P equals nRT over V from this into here. So we actually get rid of pressure. That's actually the trick with adiabatic, is the only way to do it is you get rid of pressure, you don't get rid of temperature, and then you solve for volume in terms of temperature. Remember, volume goes down means temperature goes up. Volume goes up means temperature goes down because of the work, because of work. Is colliding with the walls, or adding energy, or colliding with the walls, subtracting energy. So we have negative nRT over V dV equals 5 halves NR dt. Notice the N and the R cancel. And if I move this T over, I get negative dV over V equals 5 halves dt over T. And now I can integrate both sides. Boom, I got it. So good. Right, so what do we get? We get negative ln V plus a constant equals 5 halves ln(t), and that's just another constant. We'll combine them to that constant. And so if I take e to both sides, I get some constant we'll call k. Wait, sorry, the negative goes inside. That's what I forgot about. In fact, hold on. I want to take a step back. I think I want to move this negative over here to make this cleaner. And then I'm going to get this look more like this. It doesn't really matter that much. It's just as better. It's better. So I have k times v equals what is it? And then the negative 5/2 goes in here. So this is actually e to the natural log of t to the negative 5/2, right? And so I got that equals t to the negative 5/2. And that's our equation. Now this is a proportion constant. So we just need to plug in v1 and t1 and we get the value of k. And that will equal the same for v2 and t2. Which means, if you notice, right, by the way, t to the negative 5/2, I then multiply over, and I could get that 1 over k, if I divide it over, equals v2 times t to the, sorry, I got this, to the 5/2. There we go, got it. But 1 over k equals v1 times t1 to the 5/2, which means v1 times t1 to the 5/2 equals v2 times t2 to the 5/2. And that's how you solve for the second temperature. So if you know, like v1 is 100 milliliters, v2 is 400 milliliters, T1 is 200 Kelvin. What is T2? Well, I know if V expands, or I don't need to write the arrow there. If V expands, then T drops because work is negative for adiabatic. Remember, this is adiabatic. So Q is 0. There is no heating. There's just, I expand it. Ice piston, right? Cloud forming, right? Because work is negative, the temperature drops because of the collisions with the walls, takes energy away. Walls remove energy. Right? Remember the reasoning, right? It's not because it's more space, it's because the walls remove energy in the act of them moving away. They take energy away. So what is the new temperature though? So I should expect a lower number here. So what I do is, okay, V1 is 100. It's ratios, so I don't need to worry about units. Times 200 to the 5/2 equals 400 times T2 to the 5/2. So how do I do this? Hold on, I need a calculator. And now we just need to do little exponent rules, which is fun. So you can just plug this into your calculator. 200 to the 5/2, which is 2.5, times 100 divided by 400. So I get, careful, this is not the answer. T2 to the 5/2 is 14141.3562. Cool, I'll keep a bunch of decimals. So you're like, well, that's a big number, but that's because it's to the 5/2. So how do you do this? Well, you raise both sides to the 2/5. You raise it to the inverse of the exponent. Isn't that cool? Right? It's like if t squared equals 5, you take both sides to the 1/2 power, which is the square root. So t would equal the square root, or 5 to the 1/2, so 5. Isn't that cool? That's how exponents work. Math is so good. So I just need to take this number to the 2/5, which is 0.4. So I that to the 0.4, and I get T2 is 114.87 Kelvin. Indeed, it got colder. Now I picked a random number. That's really cold. This is really cold. I don't know why I picked those numbers. Just showing that the numbers work, that indeed the temperature dropped. Isn't that cool? And how do I get the new pressure now? Well, PV equals nRT. So P2V2 equals nRT2, right? So what I can do is I have to solve for n using P1 V1 equals NR T1, or if I'm given n, I can do that. That's from there. And then I can plug in P2 times 400 milliliters, which would be this in cubic meters, equals NR times T2, which was 114.87. And I can solve for P2 this way. Another clever thing to do is using ratios. If P1V1 over T1 equals P2V2 over T2, you can use that, hold on. V goes as T to the negative 5/2. So you can plug that in there. Sorry. We want V in terms of P. I got this. This is going to make sense. So therefore, T goes as V to the negative 2/5, which is exactly what we just saw. We go to the negative 2/5, or to the 2/5 here. And it was negative because it's an inverse function. So these are inverse, which is great. And then T goes to the negative 2/5, which then plugs in there. So I get P1V1 equals P2V2 over V to the negative 2/5. So what is 1 minus negative 2/5? Well, that means P1 times V to the, what is it? 1 minus negative 2/5, we're just doing exponent rules now, equals 7/5. So P1 V1 to the 7/5 equals P2 V2 to the 7/5 is, and this is called the adiabatic constant. This is our mu, or was it gamma? This is the adiabatic constant. And the reason why it matters is because if you add a pressure like a sound wave, how does the volume change and propagate through the medium? Right? That has to do with, this is kind of like the version of bulk modulus for air, for any gas. The adiabatic constant, I can't remember if we used mu or gamma, it doesn't matter. I think it's supposed to be mu, but I used gamma once. Yeah, same. You can pick your constant, pick your Greek letter. I picked one at different times. This is your adiabatic constant to the 7/5. And if we were to graph it, these isotherms are P goes as V to the negative 1, P goes as V to the negative 7/5, goes from 0.1 here to 0.2 here. And that's our adiabatic graph. We're going to do more of that next week or later on, but adiabatics go drop in temperature, drop in pressure. So you have a drop in temperature and a drop in pressure. What does that look like? This is what it looks like. Cool. That's what it looks like. So this is kind of these are the formulas we want. This one and this one. And this is what the graph looks like between isotherms. I can draw that a little better. If I have, T1 and T2, this really should be a little better than that. And I have 0.1 and 0.2 adiabatic expansion. Delta V is positive, so work is negative. So T drops. Did T go down? Yes, T2 is less than T1. I'm going from 0.1 to 0.2. And this should be a graph of P goes as V to the negative 7/5, which is steeper than V to the negative 1. Power law. I hope that was illuminating. I hope that made sense. Stop it, rewind it. That was cool stuff. See you later.